Let me introduce the last talk of this session. So, Alexander Perminov will talk about the orbital evolution of the four-planetary system, Sun, Jupiter, Saturn, Uranus, Neptune, on long time scales.
Good evening. I'm Alexander Perminov. I'm a postgraduate student from the Ural Federal University in Yekaterinburg, Russia. My scientific supervisor is Eduard Kuznetsov. Let's talk briefly about subject of this research. Firstly, we expand the Hamiltonian of four-planetary problem into the Poisson series in all orbital elements. We use the second system of Poincar elements and Jacobi coordinate system for it. The construction of averaged Hamiltonian and motion equations in averaged elements is performed by Hori-Deprit method. And finally, these motion equations are numerically integrated by Everhard method on long time scales up to 10 billion years. Jacobi coordinates system is more convenient for the investigation of planetary problem. In this case, the distributing function is written in more simple case. It is hierarchical coordinate system in which the position of each following body is determined relative to a center of inertia of previously including body set. The Hamiltonian of the problem in Jacobi coordinates can be expressed as shown here. This is undistributed part of the Hamiltonian which presents the interaction between the star and a planet. In the braces we have the distributing function of the problem which describes the interaction between planets. Double sum is the main part of the distributing function and single sum is the second part of the distributing function. Quantity which denoted as mu is a small parameter of the problem. It is a ratio of sum of planet masses to the mass of the star. For solar system, the value of mu can take equal to 1,000. It is the expansion parameter. We use the second system of Poincar elements for the construction of Hamiltonian expansion. It allows sufficiently simplifying an angular part of the series expansion. In this case, we have only one angular element, mean longitude. Poincar elements are canonical elements. Elements xi and eta first are proportional to the eccentricity of the orbit and called eccentric elements. Elements xi and eta second are proportional to the inclination of orbit and called oblique elements. We used computer algebra system Piranha for the construction of the Hamiltonian expansion and implementation of the algorithm of Hori-Deprit method. Piranha is an echelon Poisson series processor. The author of this program is Francesca Biscani from Interdisciplinary Center of Scientific Computing in Heidelberg. It should be noted that in the process of analytical manipulations, all orbital elements and mass parameters are received in series expansion as a simple variables. Series coefficients are rational numbers with arbitrary precision. They have integer numerators and denominators. Let's consider the algorithm of the Hamiltonian expansion. Firstly, we implemented a simple Poincar processor for the construction of expansions for Cartesian coordinates, the distance from the origin to the planetary position, ratio of distances, and scalar products. This is inverse absolute value of the difference between two Jacobi radius vectors. It is expanded into the series through Legendre polynomials. And then Legendre polynomials can be expressed through Poincar elements. Both terms of the distributing function, main part and the second part, can be expressed as series in small parameter and Poincar elements. Quantities A, B, C, and D are introduced for simplicity. Properties of the Hamiltonian expansion are given in this table. We can see here maximum degree of eccentric and oblique elements, maximum orders of Legendre polynomials which are used in the series expansion, the number of terms of series expansion, and relative accuracy of series expansion. It should be noted only that the relative accuracy of the Hamiltonian expansion is equal to 10 to the power minus 12. In this case, the relative accuracy is a relative difference between evaluated Hamiltonian and evaluated Hamiltonian expansion. We use Hori-Deprit method for the construction of averaged Hamiltonian and motion equations in averaged elements. Hori-Deprit method is based on using of Poisson brackets and theory of Lie transformation. It allows to exclude short periodic perturbations from oscillating Hamiltonian. The averaging transformation performed with respect to the mean longitudes, and the averaged Hamiltonian can be constructed as a series in small parameter. The motion equations are constructed in averaged elements. The transformation between averaged and oscillating elements are given by the functions for the change of variables. Using of averaged motion equations allows to sufficiently increase the time step of the integration. In these tables we can see a number of terms of the constructed series for Hamiltonian expansion, for motion equations, for functions for the change of variables, for all elements. Next. The integration of the motion equations in averaged Poincar elements is performed by Everhard method of 15th order for both approximations of the motion theory. Time interval of integration is 10 billion years and step is 10,000 years. Averaged Poincar elements are obtained using of the functions for the change of variables in the second approximation. And averaged Kepler and Poincaré orbital elements of solar system giant planets are given in this table in Jacobi coordinates with respect to mean ecliptic and equinoctial J2000s. Let's consider the results of integration. Upper figures are represented the evolution of eccentric elements, left picture, and oblique elements, right picture, for the first order of motion theory on time interval 2 million years and 5 million years correspondingly. Lower figures are represented the evolution of eccentric and oblique elements for the second order of motion theory. Eccentric and oblique elements save small values over whole time of the integration. Let's consider the evolution of eccentric elements for Uranus and Neptune orbits. Upper figure are represented the evolution of eccentric element Xi first for Uranus orbit on time interval 1.6 million years for both approximations of motion theory. Lower figure are represented the evolution of element Xi first for the Neptune's orbit. Dashed lines correspond to first order of motion theory, and solid line correspond to second order of motion theory. We can see that the periods of the change of eccentric elements are greatly reduced in the second approximation of motion theory. These qualitative differences between evolution of eccentric elements in both orders of motion theory explain the presence of small denominators in the motion equations of the second order. Let's consider the evolution of eccentricities. The upper figure are represented eccentricities of giant planets of solar system on time interval 1.6 million years in the first order of motion theory. In the lower figure we can see the evolution of eccentricities for the second order of motion theory. Main periods and amplitudes of the change of eccentricities are represented in these tables. We can see qualitative difference between the evolution of eccentricities for Uranus and Neptune orbits for both approximations of motion theory. Denominators which give maximum contribution to the motion equations of the second order theory are given in this table. The greatest contribution in the difference between two orders of motion theory give this denominator. If, for example, if we take out these terms with these denominators from motion equations, the orbital evolution of Uranus and Neptune's eccentricities will be close to the case of the first order theory. It is possible to exclude the influence of small denominators by transferring them to the third approximation of the motion theory. Next. In the slide, evolution of inclinations, lower figure presented the evolution of inclinations on time interval 1.6 million years for the first order theory, and lower figure represented the evolution of inclinations for the second order theory. Periods of the change of inclinations are slowly reduced in the second order of theory. In this slide we can see the evolution of ascending nodes. Evolution of ascending nodes on time interval 10 billion years shows the secular motion of the mean value of ascending nodes for all orbits. The initial value, mean value of ascending nodes is 107 degrees and 32 minutes, and the rate of the change is this mean value is 1 degree per 1 billion years for the theory of first order, and 36 minutes per 1 billion year for second order theory for all orbits. Let's consider the evolution of arguments of pericenter. Evolution of argument of pericenter for the first order theory has rotational character with various periods for all orbits. For example, for orbits of Uranus in this picture. Dashed line is first order and solid line is second order. Evolution of argument of pericenter for the second order theory has two different modes. Orbits of Jupiter, Saturn and Uranus have rotational character of the change of argument of pericenter, but orbit of Neptune has two switching modes, librational and rotational. In the first order theory, argument of pericenter have rotational mode, and the second order theory, argument of pericenter switching between librational and rotational modes. In the conclusion, let's consider the precision of the integration. In the process of the integration, the integral of energy says with relative accuracy is about 10 to the power minus 15 on time interval 10 billion years for both orders of theory. That component of the integral of areas says with relative accuracy is about 10 to the power minus 15 for the first theory order, and more precisely for the second order theory. X and y component of the integral of areas don't say. And conclusion. The expansion of the Hamiltonian of four-planetary system into the Poisson series is constructed up to second degree of small parameter. The accuracy estimation of the Hamiltonian expansion is about 10 to the power minus 12. The motion equations in averaged elements are reconstructed up to second degree of small parameter. The motion equations are integrated, and the planetary motion has an almost periodic character. Eccentricities and inclinations of the planetary orbits have small values. The short-term perturbations remain small over the entire period of the integration. Next step is the construction, the motion theory of the third approximation, and this semi-analytical motion theory will be used for the investigation of dynamic and resonant properties of extrasolar planetary systems. Thank you for attention.
We have time for some questions or remarks. Christos.
Well, just a small comment that, let's say, the most dangerous divisor could be 2/5 for Jupiter and Saturn, and I think that one was considered already by Laplace. So it means that the divisors 1/2 and 1/3 are not the most dangerous ones.
Yeah, later. Later again.
What?
Oh, there.
Yeah, but these are for the secular motions.
Well, you average over short periods, but you have the great inequality.
Yeah, yeah. So,
Скажи, по-простому. Товарищ говорит, что самое главное резонанс 2 к 5. А у тебя его тут нет. Скажи, что он вовсе и не главный.
We have not resonant 2/5 for Jupiter and Saturn because these terms are excluded from our calculations. So.
I think it is not very small.
At all.
Yes, the period is very small. 800 years only.
So it's clearly
So it-
smaller divisor than those
Yes, it is
appearing.
rotating, it is not vibration and such.
Problem is the effect on the second order effect on the frequencies.
Yes, but he calculated second order. And in second order, this resonance has is not very important.
Yes.
So you see, the much more important is the resonance 1 to 2, Uranus and Neptune.
Yes, yes.
I don't actually agree, but for Jupiter and Saturn, I completely.
After his calculations, it is not very small.
but these are the secular frequencies or
No, these are
the mean motion frequencies.
mean motion. When we speak about average.
Yes, mean motions, yes.
If you average the Hamiltonian over a short period.
Yeah, so it should be the resonances on the secular dynamics.
The resonance,
You
the
see,
mean motion
the influence of such a resonance is not in the average equations, but in the connection between
the
oscillating and mean elements.
Not only.
No,
Because when you kill
This
some
correction
elements-
was already done by Brouwer.
Exactly, and even before.
But he added also 1 to 2 and 2 to 1.
This one is.
So I think that the classical works on secular theory tells us that at least the basic mean motion resonances of this type of Saturn and Jupiter cannot be averaged. That's the
So it needs to make some experiments so to leave this term in the Hamiltonian,
Exactly.
or to throw it to the connection between oscillating and so Hamiltonian or generating function. So the concept is
it's not
to
exactly the
make
same.
two possibilities and compare these two.
Formally, if the divisor is not equal to 0, you can always remove it from the Hamiltonian. But that's only formal, because then you have to test the validity of this model against reality.
Yeah, and are there more questions? Because I have one related to
One
the-
comment.
Okay.
Actually, 10 raised to minus 16 is smallest. 10 raised to minus 16 is smallest representable number in double precision system. You have written 10 raised to suppose it's minus 70. So it will be out of the range of the representable number. So it will
Ah,
generate very
It
big
is,
error.
it is printable.
It's a divisor, so it's going to be, it's on the denominator. So it's
So-
a big effect.
No, in our system.
Now, you have problems if you add this kind of terms, so small, to a term that is of order of unity, because of the round-off errors, and then it will not have any effect. But by itself, in the divisor, okay, the divisor can be also smaller. And I have a question related to the last remark. I was expecting to have a comparison between your
Yes.
computations of the ephemerides
Yes.
with a numerical integration of the complete
Yes. Yes.
system. So in order to check the error.
Can I add to that question? Because
But,
I have the
this is-
same question. I would add that the numerical results from JPL currently cover 30,000 years. So it's long enough time span to be tested against.
Exactly.
We compare with result of numerical motion theory by integrating this Cole-Sturmer method. This is the results of Cole-Sturmer method and results of our theory, first order and second order.
Ah, okay. Well, there are differences. Is more than 10%. What is? Okay. Are there more questions or remarks? So let me thank the last speaker.